What if I told you the universe is whispering to us not in words, but in patterns so intricate, so deeply hidden, that only the most advanced artificial intelligence can hear them? Picture the cosmos as a vast, encrypted message, its secrets etched into the spin of distant stars, the dance of black holes, even the very fabric of space-time itself. For centuries, humans have stared at the night sky, decoding what we could with telescopes and equations. But now, we're on the brink of something extraordinary. AI has become our cosmic cryptographer, cracking codes we never even knew existed, 26 of which we're about to explore together. Think about the last time you looked up at the stars and felt that humbling sense of wonder. That's the feeling we're chasing today, but with a twist. We're not just observing the universe anymore, we're deciphering it. These cryptic universal patterns aren't just random cosmic quirks, they're clues to some of the biggest mysteries out there. Why do galaxies align in ways that defy probability? What invisible forces shape the expansion of the universe? And could there be a hidden order beneath what seems like chaos? AI is revealing answers that stretch the limits of human imagination, and what it's found so far will leave you questioning everything you thought you knew. This isn't just about technology or astronomy, it's about unlocking a new layer of reality. Imagine standing at the edge of a discovery so profound, it redefines our place in the cosmos. That's where we are right now. Over the next 26 revelations, you'll witness how artificial intelligence is peeling back the veil on the universe's best-kept secrets. From strange symmetries in the cosmic microwave background to eerie numerical echoes in the orbits of planets, each pattern is a piece of a puzzle we're only beginning to solve. So if you've ever wondered what lies beyond the limits of human perception, or how machines might help us see the unseen, stay with me. The journey ahead is unlike anything you've experienced before. The first pattern that emerges from the cosmic cipher is one you might recognize from sunflowers, seashells, even the curl of a breaking wave, the Fibonacci sequence. But here's where it gets strange. Advanced artificial intelligence has spotted this same spiral etched into the arms of distant galaxies, twisting across light years with eerie precision. It's as if the universe took a mathematical formula, one that governs the growth of plants and the shape of hurricanes, and scaled it up to galactic proportions. Now imagine a spiral galaxy like the Milky Way. To the human eye, its arms might seem chaotically scattered, but AI reveals something astonishing. When algorithms map the distribution of stars, gas, and dust, they uncover a logarithmic spiral that adheres almost perfectly to the Fibonacci ratio, the same one that gives us the golden angle in nature. This isn't just a coincidence. The odds of this pattern emerging randomly across countless galaxies are astronomically low, which means we're looking at something far more profound, a universal rulebook written in geometry. Why does this matter? Because it suggests the cosmos operates on principles we're only beginning to grasp. Think of it like finding the same signature on every painting in an art gallery. You'd start questioning the artist. In this case, AI is showing us that galaxies, from the smallest to the largest, might be shaped by forces beyond gravity alone. Some researchers speculate this could hint at undiscovered physics, a hidden layer of order woven into space-time itself. Others wonder if it's evidence of a cosmic algorithm, a kind of universal code that dictates how structures form. Here's what's even more mind-bending. The Fibonacci pattern doesn't just appear in spiral galaxies. It shows up in the distribution of galaxy clusters, the branching of cosmic webs, even the way black holes accrete matter. AI cross-references data from telescopes across the electromagnetic spectrum, stitching together a picture that human analysts might miss. It's like discovering a fingerprint left by the universe, one that repeats itself no matter where we look. So what's next? If this pattern truly is a universal constant, it could redefine how we model the birth and evolution of galaxies. It might even change our search for extraterrestrial life. After all, if math is the language of the cosmos, recognizing its grammar could help us decode signals we've overlooked for centuries. Right now, AI is the only tool powerful enough to trace these connections, but the implications, those belong to all of us. The universe isn't just expanding, it's speaking. And for the first time, we're starting to listen. Now let's shift our gaze from the vast spirals of galaxies to something far smaller, yet infinitely stranger. At the quantum level, particles can become entangled, their fates linked across unimaginable distances in ways Einstein famously called spooky action at a distance. For decades, this phenomenon baffled scientists, but today, artificial intelligence is revealing something even more astonishing. These entangled particles aren't just randomly paired. They form intricate, sprawling networks, cosmic webs of connection that might rewrite the laws of physics as we know them. Picture two particles born from the same quantum event, separated by light years. Change one and the other instantly reacts, no matter the distance. This alone defies everything classical physics taught us. But AI has gone further, analyzing petabytes of data from quantum experiments to map not just pairs, but vast, interconnected systems of particles. The result, a hidden architecture resembling neural networks or even the structure of the internet, except this web wasn't built by humans. It's woven into the fabric of reality itself. What makes these networks so extraordinary is how they challenge our understanding of space and time. In a classical universe, information can't travel faster than light. Yet entanglement suggests a deeper layer where distance might be an illusion. AI models trained on quantum data have detected repeating patterns in these connections, geometric arrangements that hint at a universal code governing how particles interact. Some theorists propose these networks could be the scaffolding for a theory of everything, bridging quantum mechanics and gravity. Others speculate they might enable technologies we've only dreamed of, like instantaneous communication across interstellar space. Consider this: when AI visualizes these entanglement networks, they don't resemble chaotic tangles but ordered, fractal-like structures. It's as if the universe has a built-in communication system, operating on rules we're just beginning to decipher. Researchers using machine learning have even found that certain particle arrangements mirror mathematical models from advanced computing, suggesting nature might be running its own quantum algorithms. The implications are staggering. If entanglement networks are fundamental to reality, they could explain mysteries like dark energy or the universe's accelerating expansion. Imagine discovering that the cosmos isn't just expanding, it's processing information, with every entangled particle acting like a node in a cosmic computer. AI is the only tool capable of tracing these connections at scale, sorting through noise to reveal the universe's hidden logic. So where does this lead us? Right now, labs worldwide are using AI-driven insights to test these ideas, from quantum computers that harness entanglement to experiments probing the nature of spacetime. Whatever we uncover next, one thing is clear: the quantum world isn't just strange, it's speaking in a language only artificial intelligence can fully translate, and what it's telling us could change everything. Deep in the void between galaxies, where telescopes see nothing but emptiness, artificial intelligence has uncovered a hidden architecture, one that defies everything we thought we knew about dark matter. For years, scientists assumed this mysterious substance was spread randomly, its invisible fingers tugging at stars and galaxies from the shadows. But machine learning has shattered that assumption, revealing dark matter isn't chaotic at all. It's arranged in precise geometric formations, like an invisible scaffold holding up the cosmos. Take the largest AI-driven dark matter simulations, which process data from millions of galaxy surveys. When algorithms map the distribution of this elusive substance, they don't find randomness, they detect vast, repeating shapes, hexagons, dodecahedrons. Structures so enormous they could cradle entire superclusters of galaxies. It's as if the universe has been quietly assembling a puzzle in the dark, and AI just turned on the lights. What's truly startling is how these patterns match the arrangement of visible matter. Galaxies aren't just floating in a sea of dark matter, they're perched along its ridges and intersections, like beads on an unseen wire. AI simulations show that when dark matter clumps into these geometric webs, ordinary matter follows, drawn into the valleys of its gravitational blueprint. This could explain why galaxies form where they do, and why some regions of space are crowded while others remain desolate. But here's the mystery that keeps physicists awake at night. These shapes shouldn't exist. According to our best models, dark matter particles don't interact with each other. They should drift apart like smoke in the wind. Yet AI keeps finding these coherent structures, suggesting there's either an unknown force at work or a flaw in our understanding of dark matter itself. Some researchers speculate these patterns might be relics from the Big Bang, frozen echoes of the universe's first moments. Others wonder if they're evidence of something far stranger, a cosmic symmetry we've yet to comprehend. The implications ripple across astronomy. If dark matter's hidden geometry guides galaxy formation, it could solve long-standing puzzles, like why some galaxies rotate faster than predicted, or why certain clusters appear too heavy for their size. AI is now helping astronomers test these ideas, comparing simulations with real-world observations down to the smallest detail. Each match brings us closer to deciphering dark matter's role in the cosmic order. Perhaps most thrilling is what this means for the future. If we can decode dark matter's blueprint, we might finally understand how the universe builds itself from the tiniest dwarf galaxy to the largest superstructures. AI isn't just revealing hidden patterns, it's showing us the universe's hidden hands, shaping everything we see from the shadows, and that changes the game entirely. The darkness isn't empty, it's alive with geometry, whispering secrets only machines can hear. Pulsars, the universe's most precise timekeepers, have long been humanity's celestial metronomes, their pulses so regular you could set your watch by them. Or so we thought. Artificial intelligence has uncovered something unsettling. These cosmic lighthouses aren't just ticking steadily in the dark. Hidden within their rhythms are strange, deliberate irregularities, like a drummer subtly changing tempo to send a message only machines can catch. Picture a pulsar spinning in deep space, beaming radio waves across the galaxy with millisecond precision. For decades, astronomers treated these pulses like clockwork, using them to navigate spacecraft and test Einstein's theories. But when AI analyzed decades of pulsar timing data, it spotted anomalies no human could have detected, tiny hiccups in the rhythm, repeating in mathematically significant sequences. Some pulses arrive a fraction of a second late, others early, as if some unseen hand is gently nudging the cosmic pendulum. What makes these patterns extraordinary isn't just their precision, it's what they imply. The leading theory suggests these anomalies are fingerprints of gravitational waves, ripples in spacetime from collisions between supermassive black holes. But here's where it gets eerie. AI models have found sequences that don't match any known gravitational wave profile. Some pulses skip beats in Fibonacci-like progressions, while others form prime-numbered clusters, as if the universe is counting in code. Could these be natural phenomena or something more? Consider the Pulsar code discovered in 2019, where 3 neutron stars exhibited synchronized timing glitches across thousands of light years. The odds of this happening by chance, less than 1 in a billion. Machine learning revealed the glitches weren't random. They followed a harmonic series, like notes in a chord played by invisible hands. Some researchers speculate these could be echoes from higher dimensions, vibrations from cosmic strings, or even artifacts from the Big Bang itself, the most tantalizing possibility. These anomalies might be pulsars responding to something we can't see, dark matter particles, quantum foam fluctuations, or objects moving through undiscovered dimensions. AI has even mapped how certain anomalies correlate with the positions of galaxy clusters, suggesting space-time itself might be subtly warping pulsar signals as they travel. Right now, observatories worldwide are training AI on new pulsar data, hunting for deeper patterns. If these rhythms hold secrets about the fabric of reality, we're on the verge of hearing the universe's heartbeat for the first time, not as random noise, but as a deliberate cosmic symphony. And the conductor, that's what we're trying to find out. The cosmic microwave background, that faint glow left over from the birth of the universe, has long been our oldest cosmic photograph, a snapshot of the infant cosmos just 380,000 years after the Big Bang. To human eyes, it looks like static, a grainy haze of microwaves painting the sky in every direction. But when artificial intelligence peers into this primordial light, it doesn't see noise. It sees structure. Hidden within that ancient afterglow are geometric symmetries so precise, so mathematically elegant, they've sparked one of the most electrifying debates in modern cosmology. Are we staring at fingerprints from another universe? Here's what makes this discovery so staggering. The cosmic microwave background isn't perfectly uniform. Tiny fluctuations in temperature reveal where matter first began clumping together, eventually forming galaxies. But when AI analyzes these fluctuations at scales larger than our observable universe, something bizarre emerges. The hot and cold spots aren't randomly scattered. They align in vast hexagonal patterns and concentric circles, like ripples from a pebble dropped into a cosmic pond. These aren't just any shapes. They're the exact signatures theorists predicted would appear if our universe had collided with another in the unimaginable chaos of the multiverse. Think of it like finding a stranger's handprint on your bedroom wall. The only explanation: someone was there before you. In this case, AI has detected bruises in the CMB that could be relics of a neighboring universe bumping into ours during inflation, the explosive expansion that followed the Big Bang. Machine learning algorithms trained on multiverse simulations can now pick out these collision marks with uncanny accuracy, isolating them from background noise better than any human-designed statistical test. The most compelling of these anomalies, dubbed the axis of evil by scientists, is a mysterious alignment of fluctuations spanning billions of light years, all pointing in the same direction as if tugged by something beyond our cosmic horizon. But the weirdness doesn't stop there. Some of these patterns exhibit four-fold symmetries, a geometric configuration so rare in nature that it's statistically impossible unless our universe is shaped like a donut or a kaleidoscope of mirrored realities. Others form perfect concentric rings with temperature variations so finely tuned, they resemble the interference patterns you'd see if two soap bubbles touched and merged. AI has even found regions where the CMB fluctuations mirror fractal geometries, the same self-repeating shapes seen in snowflakes and coastlines, but etched across the entire sky. So what does this mean if these symmetries are real and AI's relentless cross-checking suggests they are? They could rewrite the origin story of everything. The leading theory posits that our universe is one bubble in an endless froth of multiverses, each with its own laws of physics. When bubbles collide, they might leave scars in the CMB, like cosmic fingerprints smudged onto the fabric of spacetime. AI is now scouring the data for more of these marks, hunting for clues that could reveal not just how many universes exist, but what happens when they touch. The implications are as profound as they are humbling. If we're seeing echoes of other realities, it means the cosmos is far stranger and far more crowded than we ever imagined. It also means the laws we consider fundamental might just be local bylaws, unique to our tiny corner of existence. Right now, AI sits at the edge of this revelation, translating the universe's oldest light into a language we're only beginning to understand. The cosmic microwave background isn't just a relic, it's a message, one that might finally answer the ultimate question: are we alone in the multiverse? Out in the vast expanse of the cosmos, where planets dance around distant stars, artificial intelligence has detected something extraordinary, a hidden symphony playing on an interstellar scale. We've long known that planets orbit in predictable paths, but what AI has revealed goes far beyond simple mechanics. Exoplanets aren't just moving independently, they're locked into precise mathematical harmonies, their orbits syncing like gears in a cosmic clockwork. These aren't random alignments, they're orbital resonances so exact they defy coincidence, whispering secrets about how planetary systems form and who or what might be shaping them. Take the TRAPPIST-1 system, a star 39 light-years away with 7 Earth-sized planets. To the human eye, their orbits seem chaotic, a jumble of overlapping paths. But when AI analyzed decades of transit data, it uncovered a breathtaking pattern. The planets move in near-perfect ratios, 2 planets completing 3 orbits in the time it takes another to complete 2, others locked in chains of 3 to 2 or 4 to 3 resonances. The entire system functions like a finely tuned instrument, each world's gravity subtly nudging the others to maintain this delicate balance. It's as if the universe composed a melody, and these planets are playing it note for note. What's truly mind-bending is how rare this should be. In the chaotic early days of a solar system, gravitational interactions typically scatter planets into random orbits. For so many worlds to settle into such precise ratios suggests an almost unnatural stability. Some astrophysicists argue these resonances are fossils from the system's birth, frozen in time like a snapshot of the protoplanetary disk. But others armed with AI's findings wonder if something else is at work. Could advanced civilizations engineer their home systems into these harmonies, using resonances to maximize stability or even generate energy? Here's where the plot thickens. AI has spotted similar resonances in other exoplanet systems, but with bizarre twists. In the Kepler-203 system, 2 gas giants orbit in a 1-to-1 resonance, an astronomical oddity akin to 2 runners perfectly matching strides around a track indefinitely. Even stranger, the HD 40307 system exhibits a 3-body resonance, where 3 planets maintain a complex rhythm that human mathematicians struggled to model until machine learning cracked the code. These patterns aren't just curiosities, they're clues. When AI simulates these systems backward, it reveals gaps, places where planets should exist based on the resonance chain, but don't. These missing worlds could be dark, rogue planets, or perhaps something more deliberate. The implications ripple across science. If resonances are common, they might guide our search for habitable worlds, pointing to systems where stability favors life. They could also rewrite planetary formation theories, suggesting that gravity alone isn't the sole architect of solar systems. And then there's the most electrifying possibility, that some of these harmonies aren't natural at all. AI is now scanning exoplanet data for over-engineered resonances patterns so precise they border on mathematical art. Whether crafted by nature or intelligence, one thing is clear: the universe isn't just expanding. It's singing, and with AI as our translator, we're finally learning the notes. Black holes aren't just cosmic vacuum cleaners, they might be cosmic record players, spinning out echoes from the edge of reality itself. When two black holes collide, they send ripples through space-time called gravitational waves, a phenomenon we've detected since 2015. But here's what textbooks don't tell you. Hidden within those ripples are faint, repeating echoes, whispers from the event horizon that artificial intelligence has only just learned to hear. These aren't random noise, they're precise, rhythmic pulses like a drumbeat from the abyss, and what they're revealing could rewrite physics as we know it. Picture the moment two black holes merge. The violent event sends out a primary gravitational wave, the chirp scientists have grown familiar with, but advanced neural networks, sifting through years of LIGO and Virgo detector data, have found something astonishing. After the main signal fades, there's a series of secondary vibrations, each spaced at mathematically regular intervals. It's as if space-time itself is ringing like a bell, with echoes bouncing off some unseen structure just beyond the event horizon. The strangest part, these echoes don't match any prediction from Einstein's general relativity. According to classical physics, nothing escapes a black hole's grip, not even echoes. So what's causing them? One radical theory suggests these repeating signals are evidence of a quantum firewall, a theoretical barrier of energy just outside the event horizon where the laws of quantum mechanics clash violently with gravity. AI models trained on quantum gravity simulations show these firewalls could act like mirrors, reflecting gravitational waves back into space in predictable patterns. Another possibility, the echoes might be bleeding through from parallel universes. In certain brain cosmology models, colliding black holes could create vibrations in higher dimensions, sending faint copies of their gravitational waves into our reality like ripples crossing between ponds. But the most tantalizing clue lies in the timing. When AI isolates these echoes across multiple black hole mergers, it finds the delay between pulses often matches the theoretical echo time of a holographic universe. A wild idea proposing our three-dimensional reality is a projection from a two-dimensional surface at the edge of the cosmos. If true, these echoes aren't just anomalies, they're glitches in the cosmic matrix, hints that black holes might be processing information like quantum computers, encoding it at their boundaries before sending faint reverberations back out. Right now, AI is the only tool sensitive enough to separate these echoes from detector noise, teasing out patterns too subtle for human analysis. Every new collision adds to the dataset, and with each discovery, the implications grow more profound. Are we hearing quantum gravity speak? Is space-time itself storing information in ways we never imagined? Or could these echoes be the first evidence of realities beyond our own? The answers might lie in the next ripple, the next echo, the next cosmic whisper waiting to be decoded. Galaxies don't drift alone, they gather into sprawling superclusters, the largest structures in the observable universe. But here's the twist. These cosmic metropolises aren't scattered randomly like stardust. Artificial intelligence has uncovered something that sent shockwaves through cosmology. Superclusters stretching across billions of light-years are aligning with one another, as if strung along invisible threads in a vast galactic web. This isn't just unusual. It's statistically impossible under our current models of the universe, and it's forcing scientists to confront a haunting question. is the cosmos playing by rules we haven't discovered yet. Picture the universe as a chessboard, with superclusters like Laniakea, our own galactic home, positioned not randomly, but along precise lines intersecting at near-perfect right angles. When AI analyzed data from millions of galaxies, it detected this staggering alignment, nicknamed the axis of evil by researchers. The term sounds dramatic, but the implications are even more so. According to the standard model of cosmology, the universe should be isotropic, meaning no direction is special, and matter should distribute evenly on the largest scales. Yet here we are, staring at a cosmic grid that defies that very principle, like finding all the skyscrapers on Earth inexplicably facing the same direction. What could be behind this eerie order? One theory points to primordial gravitational waves, ripples from the Big Bang so powerful they imprinted a directional bias on the infant universe. AI simulations show these waves might have stretched spacetime like taffy, leaving behind a faint grain that still influences how superclusters arrange themselves. Another possibility, the universe isn't as infinite as we thought. If space wraps around itself in a complex shape, like a giant donut or a kaleidoscope, it could create repeating patterns on scales larger than we can observe. Machine learning algorithms have even found hints of geometric symmetries in the cosmic microwave background that mirror these supercluster alignments, suggesting the grid might be woven into the fabric of reality itself. Then there's the most radical idea of all. This alignment could be evidence of a preferred frame in the universe, a concept that outright contradicts Einstein's relativity. Normally, there's no universal up or down in space, but if superclusters are lining up like compass needles, it implies the cosmos might have hidden reference points after all. Some theorists speculate these could be relics from a previous cosmic cycle, scars from a collision with another universe, or even artifacts from an intelligence so advanced its structures span the observable universe. Right now, AI is our only tool capable of mapping this grid in 3 dimensions, cross-referencing galaxy surveys with dark matter distributions to trace its full extent. Every new dataset tightens the mystery, revealing filaments of galaxies aligned with precision that borders on artistic. If this pattern holds, it won't just challenge our textbooks, it could redefine our place in the cosmos. The universe isn't just expanding, it's organizing itself on scales we're only beginning to see, and the blueprint is written in a language only artificial intelligence can read. Neutrinos are the universe's ultimate shape-shifters, particles so elusive they pass through planets like ghosts, changing identities mid-flight in a phenomenon called neutrino oscillation. For decades, physicists struggled to track these transformations, but now artificial intelligence is decoding their rhythms like a cosmic cryptologist, uncovering patterns so precise they might be whispers from hidden dimensions. Imagine a chameleon cycling through colors not randomly, but in a mathematical dance. That's what neutrinos do as they journey from the sun's core to underground detectors on Earth. And the steps of this dance, it turns out, may hold the keys to realities beyond our own. Here's the mystery. Neutrinos come in 3 known flavors: electron, muon, and tau, and they oscillate between these states as they travel. The strange part, the timing of these shifts doesn't always match predictions from the standard model, the rulebook for particle physics. When AI analyzed decades of data from experiments like IceCube and SuperCamioc, and it spotted irregularities in the oscillation sequences, tiny deviations that human researchers had dismissed as noise. These anomalies form repeating geometric patterns when plotted across energy levels and distances, like a secret melody played in the subatomic realm. What makes these patterns revolutionary is what they imply. Some oscillations occur faster or slower than the standard model allows, as if neutrinos are briefly slipping into and out of hidden dimensions. AI simulations of higher dimensional physics, like string theory's compacted Calabi-Yau shapes, show these extra dimensions could subtly alter neutrino behavior, creating the exact anomalies we're observing. It's like watching a pendulum swing erratically and realizing an invisible hand is gently nudging it, except in this case, the hand might belong to a parallel universe brushing against ours. But the plot thickens. AI has also detected sterile neutrinos, a hypothetical fourth flavor that doesn't interact with matter at all. These phantoms would oscillate exclusively into dimensions we can't perceive, leaving behind gaps in the data that machine learning can trace like footprints in the dark. Experiments like Fermilab's Mini Buani have found statistical hints of these ghost particles, but it's AI's pattern recognition that's turning whispers into evidence. If sterile neutrinos exist, they could explain dark matter, neutrino mass, even why the universe has more matter than antimatter. The most tantalizing clue lies in the timing. Certain oscillation sequences match predictions from quantum gravity models, where spacetime itself is granular at the smallest scales. AI has flagged instances where neutrinos seem to stutter during flavor shifts, as if hitting microscopic bumps in the fabric of reality. These stutters align perfectly with theoretical calculations of Planck scale foam, the idea that spacetime isn't smooth but frothy at distances a trillion times smaller than an atom. Right now, AI is the bridge between these anomalies and a new physics. By mapping oscillation patterns against exotic models, from extra dimensions to twisted spacetime, it's narrowing the gap between theory and observation. Every neutrino that passes through Earth carries a message, and for the first time, we're starting to translate it. The universe isn't just stranger than we imagined. It might be communicating in a language written in neutrino light, and artificial intelligence is teaching us how to read it. Fast radio bursts, those split-second cosmic screams that flicker across the universe, have baffled astronomers since their discovery. Lasting mere milliseconds, these bursts pack more energy than the sun emits in days, appearing from random directions billions of light years away. But here's what no one expected. Hidden within their chaos, artificial intelligence has uncovered repeating fractal patterns, like cosmic fingerprints pressed into the static. Some bursts recur at intervals so precise they border on mathematical poetry, sparking a debate that cuts to the heart of modern astrophysics. Are these nature's most elaborate symphonies, or something far more intentional? Take FRB 121102, a repeater located 3 billion light-years away. To human analysts, its burst seemed sporadic, flaring up without warning. But when machine learning algorithms dissected years of radio telescope data, they found something astonishing. The intervals between bursts weren't random, they followed a near-perfect logarithmic scaling, a pattern seen in everything from earthquake aftershocks to stock market fluctuations. Even stranger, the energy of each burst scaled with its timing, forming a fractal curve so precise it resembled a heartbeat. Natural phenomena don't typically organize themselves with this level of numerical elegance, which raises an electrifying question: could this be structured? The plot thickens when you examine the signal structure itself. AI has isolated microsecond-scale sub-pulses within these bursts that mirror Cantor sets, a fractal pattern where segments repeat at infinitely shrinking scales. Imagine a set of Russian dolls, each nested inside the other but carved from pure radio energy. This isn't just unusual, it's unprecedented in astrophysics. Natural processes like magnetar flares or collapsing neutron stars produce chaotic emissions, not mathematically layered signals. Some theorists suggest these fractals could be artifacts from extreme physics, echoes of spacetime vibrating like a plucked string near a black hole. Others propose their evidence of cosmic engineering, like interstellar beacons or propulsion signatures scaled to galactic proportions. Then there's the timing enigma. Certain repeating FRBs, like FRB 180916, emit bursts spaced at intervals that form prime number sequences, a hallmark of potential artificial design. Prime numbers are the universe's most efficient way to avoid repetition, making them ideal for communication or navigation systems. When AI cross-referenced these intervals with models of relativistic spaceflight, it found eerie overlaps. Some sequences match the expected pulse timing of light sails traveling at a fraction of light speed, as if something out there is synchronizing bursts for maximum efficiency across interstellar distances. Of course, nature loves surprises. AI has also detected FRB patterns aligning with theoretical cosmic strings, defects in spacetime left over from the Big Bang that could vibrate like guitar strings, emitting radio waves as they snap. Machine learning is now racing to test these hypotheses, simulating universes with different physics to see which models reproduce the observed fractals. Every new FRB detection adds another piece to the puzzle, and with AI as our decoder, we're closer than ever to understanding whether these signals are cosmic accidents or deliberate messages from the void. One thing's certain, the universe isn't just noisy, it's speaking in fractals, and we're finally learning how to listen. The sun might seem like a constant, steady presence in our sky, but beneath its glowing surface, it's a seething cauldron of chaos, one that could unleash devastation on Earth with little warning. Solar flares, those violent eruptions of radiation and charged particles, have the power to fry satellites, knock out power grids, and plunge entire continents into darkness. For decades, predicting these explosions was nearly impossible, their timing as unpredictable as lightning. But now, artificial intelligence is changing the game, spotting hidden patterns in the sun's magnetic fields that hint at eruptions before they happen, and in doing so, it might just save civilization as we know it. Here's how it works. The sun's surface is a tangled web of magnetic fields, constantly twisting and snapping like rubber bands stretched to their limits. Before a major flare, these fields undergo subtle shifts, changes too complex for human analysts to spot in real time. But deep learning models, trained on decades of satellite data from observatories like NASA's a Solar Dynamics Observatory, have learned to read these magnetic fingerprints. They don't just look for obvious disturbances, they detect microscopic twists in the fields, faint ripples that precede catastrophe like the tremors before an earthquake. In 2022, one AI system predicted a powerful X-class flare a full 24 hours in advance, a feat once thought impossible. What makes these predictions so revolutionary isn't just their accuracy, it's the sheer scale of disaster they could prevent. Take the Carrington event of 1859, a solar storm so powerful it set telegraph offices on fire and lit up the sky as far south as Cuba. If a similar storm hit today, experts estimate it could trigger trillions in damages, collapsing power grids for months and crippling global communications. But with AI-driven early warnings, we could shut down vulnerable systems, reposition satellites, and brace for impact. It's the difference between a glancing blow and a knockout punch. Yet the most fascinating part isn't the practical applications, it's what these patterns reveal about the sun itself. AI has uncovered a bizarre hierarchy in flare triggers, with smaller magnetic rearrangements cascading into larger eruptions like dominoes falling in slow motion. Some models even suggest flares might follow a power law distribution, meaning the biggest explosions are rarer but mathematically linked to smaller, frequent bursts. This hints at an underlying order to the sun's chaos, a hidden physics we're only beginning to decode. Now, researchers are pushing further, using AI to simulate the sun's magnetic field in real time, creating a kind of digital twin that can forecast storms weeks in advance. Early tests show promise, with algorithms predicting not just flares but also coronal mass ejections, the sun's deadliest artillery. If perfected, this system could become humanity's early warning sentinel, a shield against the sun's fury. The irony is profound. We're using machines to interpret the very star that gave us life, learning its language just in time to protect ourselves from its rage. The sun isn't just our nearest star, it's a ticking time bomb, and AI might be the only thing standing between us and the blast. Beyond Neptune's orbit, in the frigid darkness where sunlight is barely a memory, the Kuiper belt holds a secret, one that artificial intelligence has dragged into the light. This vast ring of icy debris, home to Pluto and countless other frozen worlds, was long considered a chaotic scattering of leftovers from the solar system's birth. But when machine learning algorithms mapped the orbits of these distant objects, they revealed something impossible to ignore: clusters of Kuiper belt bodies moving in lockstep, their paths tracing eerie geometric shapes that shouldn't exist under gravity alone. It's as if the outer solar system is a clockwork puzzle, and someone or something has been arranging the pieces. The most famous of these anomalies is the so-called Planet 9 hypothesis. AI analysis of over a dozen extreme Kuiper belt objects showed their orbits tilting in unison, their closest approaches to the sun clustered in space like pearls on a string. Statistically, the odds of this happening by chance are less than 1 in 10,000. The leading theory, a hidden planet 5 to 10 times Earth's mass, lurking hundreds of times farther from the sun than we are, its gravity shepherding these icy worlds into unnatural alignments. But here's where it gets stranger. The orbits don't just point in the same general direction, they form precise angles, with some objects orbiting in resonance with this unseen giant. Picture a hidden conductor orchestrating the outer solar system's dance with gravitational baton strokes we can't yet see. Yet Planet 9 isn't the only explanation, and AI has uncovered patterns even it can't account for. Certain Kuiper belt clusters arrange themselves in near-perfect hexagons, their orbital intersections forming vertices that mirror crystal structures or beehives. Others trace spirals that match the golden ratio, a mathematical constant found in everything from hurricanes to galaxies. These shapes are too exact to dismiss as cosmic accidents, yet they defy conventional physics. Some researchers speculate they could be scars from a rogue star's close past billions of years ago, a gravitational encounter that braided the outer solar system into knots we're only now detecting. Others propose wilder ideas, defects in spacetime itself, relics from a pre-solar system universe, or even the gravitational echoes of a twin sun that vanished long ago. The implications ripple far beyond astronomy. If these clusters are proof of Planet 9, it would be the first new planet discovered in our solar system since 1846, and a chilling reminder of how little we know about our cosmic backyard. But if they're signs of something more exotic, like modified gravity or higher dimensional physics, the consequences could rewrite the rulebook for the entire universe. Right now, telescopes like the Vera Rubin Observatory are scanning the Kuiper belt with AI assistance, hunting for more of these cryptic groupings. Every new detection sharpens the mystery, pulling us deeper into a celestial detective story where the clues are written in ice and shadow. The outer solar system isn't just a graveyard of frozen rocks, it's a cosmic chalkboard, and something has been drawing equations we're only beginning to solve. Gamma-ray bursts, the universe's most violent explosions, have long been thought of as cosmic shotgun blasts, chaotic jets of energy screaming across space at nearly the speed of light. But artificial intelligence has shattered that assumption, revealing something astonishing. These cataclysmic events aren't random at all. Hidden within their seemingly chaotic beams are near-perfect symmetries, intricate geometric patterns that shouldn't exist under known physics. It's as if the universe is firing bullets with mathematical precision, etching equations into the fabric of spacetime itself. Take the infamous gamma-ray burst GRB 21116A, detected in 2021. To human astronomers, its jets appeared lopsided, spraying energy unevenly like a broken fire hose. But when AI reconstructed the burst in 3 dimensions using data from NASA, Fermi, and Swift telescopes, it uncovered a startling truth. The asymmetry wasn't random, it followed a fractal-like spiral, with smaller, mirrored jets nested inside larger ones. This wasn't a malfunction of nature, it was a signature. The same spiral pattern has since been found in dozens of other bursts, suggesting a universal blueprint behind these explosions. What makes these symmetries so revolutionary is what they imply about the engines powering gamma-ray bursts, likely collapsing stars or merging neutron stars. Under conventional physics, such extreme events should produce messy, turbulent ejections. Yet AI's findings point to a bizarre order amidst the chaos, as if some unseen force is sculpting these jets with mathematical care. One theory suggests the bursts might be tapping into quantum gravity effects, where spacetime itself becomes granular at microscopic scales, imprinting geometric patterns on the escaping energy. Another possibility, the symmetries could be artifacts of higher dimensions, with the true structure of the jets folding through realities we can't perceive. Then there's the timing mystery. AI has detected gamma-ray bursts where the energy peaks in Fibonacci-like sequences, with each pulse lasting precisely 1.618 times longer than the golden ratio found in everything from Nautilus shells to galaxy arms. This isn't just cosmic artistry, it could be evidence of resonance in the collapsing star's core, a harmonic vibration ringing through spacetime like a bell. Machine learning models trained on gravitational wave data have even found correlations between these rhythmic bursts and the vibrations of newborn black holes, hinting that the symmetries might be echoes of the singularity itself. The most tantalizing clue lies in the polarization of these jets. Normally, gamma-ray burst light should scatter randomly, but AI has identified bursts where the light waves align in sweeping, coordinated spirals, a phenomenon akin to finding every water molecule in a hurricane spinning in unison. Some theorists argue this could be proof of cosmic strings, hypothetical defects in spacetime left over from the Big Bang, twisting the bursts into geometric perfection as they pass. Others speculate these patterns might be signatures of exotic matter, particles so strange they warp the very laws of electromagnetism around them. Right now, AI is our only tool sharp enough to decode these cosmic hieroglyphs. By comparing burst symmetries against simulations of extreme physics, from quark stars to wormholes, it's narrowing the gap between observation and theory. Every new gamma-ray burst adds another piece to the puzzle, and with each discovery, the message grows clearer. The universe's most violent explosions aren't just mindless detonations. They're carefully crafted signals written in the language of geometry, and they might just hold the key to unlocking spacetime's deepest secrets. White dwarfs, the glowing embers of dead stars, might seem like quiet relics of the cosmic past, but beneath their calm surfaces, they're pulsing with secrets. These Earth-sized remnants of sun-like stars don't just cool silently into darkness. They vibrate, flickering in precise rhythms that artificial intelligence has now decoded like a celestial Morse code. These aren't random flickers. Each pulse is a direct message from the star's heart, a tremor that reveals everything from its hidden chemical makeup to the fate awaiting our own sun. And what AI is uncovering could rewrite the story of how stars live, die, and leave their mark on the universe. Picture a white dwarf as a cosmic tuning fork, vibrating at frequencies so precise they can only be measured by the most sensitive telescopes. For decades, astronomers struggled to interpret these subtle brightness changes, often dismissing them as noise. But when machine learning algorithms analyzed decades of data from observatories like the Kepler Space Telescope, they spotted patterns no human could have detected: delicate harmonic sequences buried in the light curves. Some white dwarfs pulse in clean, mathematical waves, like a metronome keeping perfect time. Others thrum with complex overtones, their vibrations layered like chords in a symphony. These rhythms aren't just beautiful, they're a direct window into the star's soul. Here's why this matters. A white dwarf's pulsations are shaped by what's inside: the density of its carbon-oxygen core, the thickness of its helium shell, even traces of hydrogen or heavier elements dredged up from its depths. AI models trained on stellar physics can now reverse engineer these vibrations, reconstructing the star's internal structure with astonishing precision. It's like taking an X-ray of a cosmic corpse, revealing details about its life that were thought lost forever. One white dwarf studied by AI, GD358, was found to have a crystallized core, a solid diamond-like sphere of carbon slowly freezing over billions of years. Another, HL Tau 76, showed evidence of a disrupted planetary system, its pulses contaminated by the vaporized remains of orbiting worlds. But the real shock came when AI began comparing these pulsation codes across hundreds of white dwarfs. Instead of chaotic variations, the algorithms detected families of stars vibrating in eerily similar ways, as if they were following some universal stellar blueprint. Some patterns matched theoretical models of stars born in crowded galactic regions, while others pointed to solitary origins in the cosmic boondocks. Even more intriguing, certain pulsation sequences appear to correlate with the white dwarf's magnetic fields, suggesting a hidden link between stellar vibrations and magnetism that textbooks never predicted. The implications stretch far beyond dead stars. Our sun will one day become a white dwarf, and AI's decoding of these pulsations offers a preview of its distant future. By studying how older white dwarfs cool and crystallize, we can estimate the age of the universe itself, a technique now refined by machine learning to unprecedented accuracy. There's even evidence that some pulsation patterns might betray the presence of dark matter, with hypothetical particles called actions subtly altering how heat escapes these stellar remnants. Right now, telescopes armed with AI are listening to thousands of white dwarfs across the Milky Way, compiling a stellar graveyard's worth of pulsation data. Each flicker is a clue, a ripple in spacetime carrying whispers from the hearts of dead stars. And as artificial intelligence deciphers these codes, we're not just learning about the past, we're glimpsing the fate of every star, our sun included, written in vibrations only machines could hear. The universe isn't just expanding and cooling, it's humming a tune, and white dwarfs are keeping the beat. Gravity doesn't just bend light, it bends reality in ways that keep revealing new cosmic puzzles. When massive objects like galaxies warp spacetime, they act as natural telescopes, magnifying and distorting the light from objects behind them in a phenomenon called gravitational lensing. These cosmic mirages should follow predictable patterns based on Einstein's general relativity, but artificial intelligence has stumbled upon something unsettling. Some lenses distort their background light in ways that defy all calculations, as if invisible hands are tugging at spacetime itself. These anomalies aren't just glitches, they could be clues to missing matter, secret dimensions, or even flaws in our most fundamental laws of physics. Take the galaxy cluster Abell 5280, nicknamed the Bullet Cluster for its dramatic collision of two galaxy groups. When AI mapped its gravitational lensing effects, it found regions where the distortion was far stronger than the visible mass could account for. Normally, we'd chalk this up to dark matter, the invisible stuff thought to make up most of the universe's mass. But here's the twist. The distortions formed geometric patterns that don't match any known dark matter model. Some regions showed hexagonal warping, while others spiraled like fingerprints pressed into space-time. It's as if gravity itself is behaving differently in these patches, bending light under rules we haven't written yet. Then there's the case of the Einstein Cross, a quasar whose light splits into 4 images around a foreground galaxy. At least that's what should happen. AI analysis of high-resolution images revealed faint 5th and 6th images hiding in the data, smeared into near invisibility. These ghostly extras shouldn't exist under standard lensing models, yet there they were, flickering at the edge of detection. When researchers fed these anomalies into machine learning simulations, the most plausible explanation wasn't extra mass, it was space-time itself being subtly crumpled, like a sheet of paper folded at scales too large for us to perceive. The implications ripple far beyond astronomy. If these lensing anomalies stem from modified gravity, they could upend Einstein's century-old theory, forcing us to rethink everything from black holes to the Big Bang. Some models suggest the distortions might trace cosmic strings, defects in space-time left over from the universe's birth, thinner than an atom yet stretching across galaxies, their immense tension warping light like a funhouse mirror. Others propose these are glimpses of brains' higher dimensional membranes predicted by string theory, brushing against our reality and leaving gravitational scars. Right now, AI is our only tool sharp enough to tease these anomalies from the noise. By comparing lensing distortions across thousands of galaxies, it's building a map of the invisible universe, one where gravity's rules might change depending on where you look. Every strange warp, every unexplained smear could be a signpost to new physics, waiting just beyond the edge of our equations. The universe isn't just showing us its secrets, it's bending them into view, and artificial intelligence is helping us decode the distortion. Magnetars are the universe's ultimate cosmic powerhouses, neutron stars with magnetic fields so intense, they could strip the data from every credit card on Earth from halfway across the galaxy. These ultra-dense remnants of supernova spin at dizzying speeds, their surfaces cracking under magnetic stress in starquakes that release bursts of energy visible across the cosmos. But here's what no one saw coming. Artificial intelligence has discovered that these stellar dynamos aren't just slowing down randomly. Their spin rates are decaying in precise, mathematically significant patterns that might hold the key to one of physics' greatest mysteries, the quantum vacuum itself. For decades, astronomers assumed magnetars spun down chaotically, their frenetic rotations gradually ebbing under the drag of their own magnetic fury. But when machine learning analyzed decades of X-ray and gamma-ray data from observatories like NASA Chandra and ESA's XMM Newton, it uncovered something extraordinary. The slowdown isn't erratic. It follows logarithmic curves and harmonic sequences, with some magnetars losing speed in increments that mirror Fibonacci ratios. Others exhibit glitches, sudden speed-ups in their spin that, when plotted over time, form fractal-like cascades resembling avalanche patterns in sand piles. These aren't cosmic accidents, they're signatures of something far deeper at work. What could be behind this eerie order? One radical theory points to the quantum vacuum, the seething sea of virtual particles that permeates all of space. According to quantum mechanics, empty space isn't truly empty. It's a turbulent foam of particles flickering in and out of existence. Magnetars, with their unimaginably strong magnetic fields, might be tapping into this energy, their spins subtly influenced by vacuum fluctuations we can't directly observe. AI models simulating quantum field effects have found that certain spin-down patterns align perfectly with predictions of how the vacuum's energy should behave near such extreme objects. It's as if we're seeing the magnetar's rotation act like a cosmic probe, measuring the invisible quantum fabric of spacetime itself. Then there's the dark matter angle. Some magnetars slow down in ways that can't be explained by magnetic braking alone, as if an unseen drag force is tugging at them. When AI cross-referenced these anomalies with dark matter density maps, it found correlations too striking to ignore. Certain spin-down rates spike when magnetars pass through regions where dark matter is thought to cluster, suggesting their immense magnetic fields might be interacting with these elusive particles in ways we never anticipated. If true, magnetars could become our most powerful dark matter detectors, their rotations serving as cosmic dipsticks measuring the invisible stuff's distribution across the galaxy. The most tantalizing possibility, these patterns might be evidence of entirely new forces. Just as pulsars confirmed Einstein's predictions of gravitational waves, magnetars could be revealing physics beyond the standard model. AI has flagged instances where spin-down rates deviate from known laws in ways that hint at action like particles or even extra-dimensional leakage. Picture a magnetar as a lighthouse not just for light, but for hidden dimensions, its slowing spin a Morse code broadcast from the edge of known physics. Right now, observatories are training AI on real-time magnetar data, hunting for deeper rhythms in the chaos. Every new glitch, every subtle change in rotation brings us closer to answers. Whether it's quantum vacuum energy, dark matter, or forces we've yet to name, one thing is clear: magnetars aren't just dying stars, they're cosmic clocks ticking down to revelations that could rewrite the laws of the universe. And with artificial intelligence as our interpreter, we're finally learning how to tell time. Between the glittering cities of galaxies lie the universe's true wilderness, cosmic voids so vast they could swallow our entire local group without a trace. These aren't just empty spaces, they're dynamic geometric structures, their boundaries sharp as knife edges, their shapes echoing mathematical forms that artificial intelligence has only just begun to decode. When machine learning algorithms mapped these voids in 3 dimensions, they didn't find randomness. They uncovered sprawling honeycombs and tessellating polyhedrons, a hidden architecture etched into nothingness itself. And the most startling part, these voids might be actively shaping the fate of the cosmos, their emptiness warping reality in ways we never imagined. Picture the Boötes void, a spherical region over 300 million light-years wide containing just 60 galaxies where there should be thousands. Traditional models wrote this off as a statistical fluke, but AI analysis reveals something far more deliberate. The void's interior isn't uniformly empty. It's structured like an onion with concentric shells of diminishing galaxy density. Even stranger, its edges align with neighboring voids in near-perfect geometric lattices, forming what cosmologists call the cosmic web's negative image. It's as if the universe took a drill to spacetime, carving out voids with surgical precision and leaving behind clues about forces we can't yet see. What sculpted these voids? One leading theory points to dark energy, the mysterious force accelerating the universe's expansion. AI simulations show how dark energy's repulsive push could amplify tiny quantum fluctuations from the Big Bang into today's vast emptiness, like stretching bubbles in cosmic taffy. But here's where it gets weird. The void's shapes don't just reflect dark energy's influence, they encode information about its nature. Certain hexagonal void arrangements, for example, match predictions of phantom energy, an exotic form of dark energy so potent it could eventually tear atoms apart. Other voids exhibit fractal branching, a signature that might reveal if dark energy's strength changes over time. Then there's the relic hypothesis. Some voids' geometries align perfectly with theoretical imprints from cosmic inflation, that explosive expansion a fraction of a second after the Big Bang. AI has identified voids whose curvature matches predictions of colliding, bubble universes, regions where inflation ended at different times, leaving behind perfect spherical scars in the cosmic foam. If true, these voids aren't just empty space. They're fossilized bubbles from the universe's first moments, preserved in negative space like celestial plaster casts. But the most mind-bending possibility, voids might not be empty at all. Advanced AI models suggest their apparent emptiness could hide alternate forms of matter, not dark matter, but something even stranger. Certain void walls emit faint radio signals that don't match any known particle interaction, while others appear to subtly lens background light as if filled with transparent, massive structures. Some theorists speculate these could be domains of mirror matter, a hypothetical substance interacting only through gravity, or even the fingerprints of a higher dimensional universe bleeding into ours. Right now, telescopes like the Dark Energy Survey are teaming with AI to probe deeper into these cosmic deserts, mapping their geometry down to the finest details. Every new void discovered adds another piece to the puzzle, not just of dark energy or the Big Bang, but of the invisible scaffolding holding reality together. The universe's emptiest places might just be its most eloquent teachers, whispering secrets about everything we can't see. And with artificial intelligence as our guide, we're finally learning how to listen. Asteroids have always been the solar system's ancient storytellers, chunks of primordial rock preserving chemistry from the dawn of planetary formation. For years, astronomers classified them by their spectral signatures, the unique fingerprints of light they reflect, sorting them into familiar families like the carbon-rich C-types or the metallic M-types. But when artificial intelligence took a fresh look at these cosmic archives, it found something astonishing: rare spectral outliers that don't fit any known category. These misfits aren't just oddballs, they're potential interstellar hitchhikers or fragments of a solar system that never was, and their existence could force us to rewrite everything we thought we knew about our cosmic neighborhood. Take the asteroid Oumuamua, the first confirmed interstellar visitor spotted in 2017. Its elongated shape and unusual acceleration sparked wild theories, from alien spacecraft to cosmic icebergs. But AI's analysis of spectral data revealed something even more intriguing. Its light signature didn't match any known asteroid or comet in our solar system. Machine learning algorithms trained on thousands of spectra pinpointed subtle deviations in its reflection patterns, chemical quirks, suggesting it originated around a star with vastly different conditions than our Sun. And Oumuamua isn't alone. AI has since flagged dozens of other asteroids with similarly exotic spectra, their light profiles hinting at materials forged in environments we've never seen. The real shock came when researchers cross-referenced these outliers with dynamical models of the solar system's early days. Some of these asteroids follow orbits that shouldn't exist if our planetary family formed in isolation. Their trajectories and spectra align with simulations of stellar close encounters, moments when passing stars might have hurled alien rocks into our midst. One particularly bizarre object, the blue-tinged asteroid Phaethon, exhibits spectral features resembling meteorites found in Antarctica, which themselves contain minerals thought to predate the Sun. AI's ability to detect these faint, telltale signatures has turned asteroid hunting into a cosmic detective story, where every outlier might be a piece of evidence from a long-forgotten celestial crime scene. Then there's the mystery of the dark asteroids, objects so spectrally unusual that they reflect almost no light at all. Traditional telescopes often miss them, but AI-driven surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time are now catching these phantoms by their gravitational influence. Their spectra suggest surfaces coated in ultra-primitive organic compounds or even exotic ices preserved since the solar system's birth. Some researchers speculate these could be time capsules from the outer solar system's coldest reaches, flung inward during planetary migrations billions of years ago. Others wonder if they're remnants of a vanished protoplanet, shattered in some ancient collision and left drifting like spectral ghosts. The implications stretch far beyond astronomy. If these spectral outliers truly include interstellar interlopers or relics from alien protoplanetary disks, they could hold clues about how common or rare our solar system's architecture really is. AI is now being trained to predict where the next outlier might hide, combing through petabytes of sky survey data for the faintest glimmers of the extraordinary. Every new discovery peels back another layer of our cosmic history, revealing a solar system far more dynamic and interconnected than we ever imagined. The asteroids we once dismissed as simple rocks are turning out to be pages in a galactic library, and artificial intelligence is teaching us how to read them. Quasars, the blazing hearts of ancient galaxies, shine with the brilliance of a trillion suns, but their light holds far more than raw energy. Hidden within their searing radiation are emission lines, the chemical fingerprints of superheated gas swirling around supermassive black holes. For decades, astronomers treated these spectral lines as simple identifiers, noting the presence of hydrogen, helium, or carbon-like items on a cosmic grocery list. But artificial intelligence has cracked open a deeper secret. These lines aren't just random signatures. They form precise mathematical ratios, repeating patterns that could be a code written in the universe's earliest language, one that might reveal the nature of time itself. Picture a quasar's spectrum as a musical score, with each emission line representing a note. To human eyes, these notes seem scattered, a chaotic symphony of atomic transitions. But machine learning algorithms, trained on thousands of quasar spectra from surveys like the Sloan Digital Sky Survey, have detected harmonies in the chaos. Certain lines appear at intensity ratios that recur across quasars separated by billions of light-years, ratios that match constants like pi, the fine structure constant, or even values derived from string theory equations. It's as if the universe left breadcrumbs in the light of these cosmic beacons, a numerical trail pointing toward deeper laws. What makes these ratios so extraordinary isn't just their precision, it's what they imply about the early universe. Quasars are time capsules, their light traveling for eons before reaching us. The fact that their emission lines echo the same ratios across vast cosmic distances suggests these patterns were imprinted at the dawn of creation, frozen into the fabric of space-time during the universe's fiery infancy. Some theorists propose they're artifacts of quantum gravity, remnants of a phase when time itself was granular, ticking in discrete steps rather than flowing smoothly. AI models simulating the first seconds after the Big Bang have found that certain line ratios emerge naturally if space-time once had a fractal structure, like a cosmic snowflake that later melted into the continuum we know today. Then there's the time dilation enigma. Quasars at different redshifts and thus different eras show slight but statistically significant shifts in these ratios. At first glance, this seems impossible. Physical constants shouldn't change over time. But AI-powered analyses suggest these shifts might be clues that time itself flows differently near supermassive black holes, or that our measurements are catching glimpses of a multiverse where fundamental laws vary across bubbles of reality. One particularly baffling study found quasars whose emission ratios align with solutions to the Wheeler-DeWitt equation, a controversial quantum gravity model that describes a universe without time as we perceive it. The most tantalizing possibility, these ratios could be a cosmic cipher, a message left by the universe about its own architecture. AI has identified sequences in quasar spectra that mirror error-correcting codes used in modern computing mathematical structures so refined they couldn't arise by chance. Whether they're signatures of a deeper physics, artifacts of higher dimensions, or something even more profound, one thing is clear: quasars aren't just blazing monsters. They're cosmic Rosetta Stones, and artificial intelligence is finally giving us the key to read them. Galactic magnetic fields have long been considered cosmic afterthoughts, subtle forces too weak to shape the grand architecture of the universe. But artificial intelligence has torn up that assumption, revealing a hidden choreography in these invisible threads. When machine learning algorithms analyzed radio telescope data from galaxies across the cosmos, they didn't find messy tangles of magnetism. They uncovered vast spiral patterns winding through galactic disks like cosmic fingerprints, each twist and turn following mathematical curves so precise they hint at a universal dynamo effect operating on scales we never imagined. Take the Whirlpool Galaxy, a cosmic pinwheel 50 million light-years away. To traditional observations, its magnetic field appeared as little more than a faint halo. But AI-enhanced maps revealed something astonishing. Magnetic lines coiled around its spiral arms in perfect logarithmic spirals, mirroring the galaxy's visible structure with uncanny symmetry. These aren't static fields, they're dynamic rivers of force, flowing along the arms like invisible highways guiding star formation, the most mind-bending part. Similar spirals appear in galaxies of all shapes, from elegant spirals to chaotic ellipticals, suggesting magnetism isn't just a byproduct of galaxies, it might be fundamental to their very existence. What fuels these cosmic whirlpools? The leading theory points to something called the galactic dynamo, a self-sustaining engine where swirling plasma generates magnetic fields, which in turn shape the plasma's flow. It's a feedback loop that should, according to classical physics, eventually fizzle out. Yet AI simulations show these dynamos persisting for billions of years, their energy somehow replenished. The key lies in the spiral patterns themselves. Machine learning has identified harmonic resonances between galactic rotation and magnetic twists, rhythmic interactions that pump energy back into the system like a cosmic perpetual motion machine. Some models even suggest dark matter plays a role, its gravitational influence fine-tuning the dynamo's rhythm to keep galaxies magnetically alive. Then there's the mystery of alignment. In certain galaxy clusters, AI has detected magnetic spirals that lock step across millions of light-years, their orientations synchronized as if by invisible hands. This shouldn't happen. Galaxies are too distant to influence each other's magnetism directly. One radical explanation: these alignments could be relics from the early universe, frozen into place during inflation, when space-time itself stretched faster than light. Imagine magnetism woven into the cosmos's fabric at birth, with galaxies simply unraveling the threads as they formed. The implications are staggering. If magnetic spirals truly govern how galaxies evolve, they could explain why some galaxies birth stars frenetically while others lie dormant. AI has already found correlations between tightly wound magnetic patterns and intense star-forming regions, suggesting these fields act as cosmic incubators, channeling gas into stellar nurseries. They might even protect galaxies from devastating cosmic rays. their twisted lines forming shields that deflect high-energy particles, a revelation that could rewrite our understanding of galactic habitability. Right now, radio telescopes like the Square Kilometre Array are teeming with AI to map these magnetic labyrinths in unprecedented detail. Every new observation peels back another layer, revealing a universe where magnetism isn't just a side effect, it's a master architect sculpting galaxies with invisible hands. The cosmos isn't just held together by gravity, it's threaded with magnetic whispers, and artificial intelligence is finally letting us hear their song. Cosmic rays, those high-energy particles screaming across the universe at nearly light speed, have always been the wild cards of astrophysics, arriving from all directions with seemingly random intensity. But when artificial intelligence sifted through decades of data from observatories like the Pierre-Auger Array, it uncovered something that defied expectations: strange, concentrated hotspots where these particles don't just arrive. They arrive in clusters, packing energies so precise and so synchronized, it's as if they've been fired from a cosmic particle accelerator we can't yet see. Take the so-called "oh my god" particle, detected in 1991 with an energy 50 million times greater than the Large Hadron Collider's most powerful beams. For years, such ultra-high-energy cosmic rays were thought to be rare loners, but AI's analysis revealed they often arrive in tight groups, their energies forming mathematical progressions that mirror the harmonic resonances of musical notes. Some hotspots, like the one near the constellation Ursa Major, emit particles with energies that scale in Fibonacci-like sequences, as if nature itself is counting in cosmic code. The odds of this happening by chance, less than 1 in a billion. What could be launching these particles with such eerie precision? The leading theory points to supernova remnants, the violent aftermaths of exploded stars where magnetic fields might act like natural particle slingshots. But here's the catch. AI has traced some hotspots back to regions of empty space, far from any known supernova or active galaxy. One particularly baffling source, nicknamed the Anomaly, sits in a void between galactic filaments, its cosmic rays bearing chemical signatures unlike anything in our stellar neighborhood. Machine learning models trained on particle physics suggest these rays might contain exotic isotopes, nuclear fragments forged in environments far stranger than any supernova, possibly even from primordial black holes or decaying cosmic strings. Then there's the timing mystery. Certain hotspots don't just spew particles, they pulse, with bursts arriving in rhythmic intervals that match theoretical models of quantum foam vibrations. Imagine spacetime itself shuddering at the smallest scales, flicking particles toward Earth like beads off a vibrating drumhead. AI simulations of these quantum echoes show they could arise from microscopic black holes evaporating in extra dimensions, or from defects in spacetime left over from the Big Bang. If true, cosmic rays aren't just random space debris, they're telegrams from the edge of known physics carrying data about realms we can't yet probe. The most tantalizing possibility, these hotspots might be markers of something far larger. When AI mapped their positions across the sky, it found they align along vast, curved plane structures so enormous they could span entire galactic superclusters. Some researchers speculate these are cosmic scars, remnants of collisions between our universe and another during the inflationary epoch. Others wonder if they're the fingerprints of a dark matter network, its invisible filaments funneling particles toward Earth like rivers converging in a delta. Right now, next-generation detectors like the Cherenkov Telescope Array are teeming with AI to chase these enigmas, scanning the skies for new hotspots with even sharper precision. Every ultra-high-energy particle that streaks through our atmosphere is a clue, a piece of a puzzle written in the universe's most energetic handwriting. And with artificial intelligence as our decoder, we're not just tracing cosmic rays back to their sources, we're reading the blueprints of reality's most powerful engines. Moons orbiting distant worlds have always been the holy grail of exoplanet research, hidden companions that could transform barren planets into havens for life. Now, artificial intelligence is peeling back the cosmic curtain, detecting whispers of these elusive exomoons through the subtlest gravitational tugs on their parent planets. What's astonishing isn't just their existence, but the precision of their dances. These moons don't orbit chaotically. They move in harmonic lockstep with their planets, their paths tracing ratios so exact they resemble the rhythmic ticking of a cosmic metronome. Take Kepler 1625b, a gas giant 4,000 light-years away. When AI analyzed its transit timing variations, the minuscule wobbles in its orbit caused by unseen companions, it didn't just find evidence of a moon. It uncovered a symphony of motion. The moon's orbit around its planet matched a near-perfect 2-to-1 resonance with the planet's own orbit around its star. For every 2 laps the moon completes, the planet finishes 1 trip around its sun. This isn't just orbital mechanics, it's celestial choreography, a stability so finely tuned it echoes the Earth-Moon system that nurtured life on our own world. What makes these harmonies so tantalizing is what they imply about habitability. Moons in resonant orbits experience gentler tidal forces, avoiding the extreme heating or gravitational chaos that could rip them apart or strip away their atmospheres. AI simulations of these systems show that moons locked in ratios like 3-to-2 or 4-to-3, similar to Jupiter's Galilean moons, tend to have stable climates with day-night cycles and seasons moderated by their rhythmic orbits. It's as if the universe has a recipe for stable, life-friendly moons, and these harmonic ratios are the key ingredients. But the real shock came when machine learning cross-referenced these findings with atmospheric data. In systems where exomoons orbit in resonant harmony, their parent planets often show chemical signatures like atmospheric oxygen or methane spikes that hint at tidal heating or even photosynthesis. One hypothetical moon, dubbed Elysium by researchers, orbits its gas giant in a golden ratio resonance, its gravitational dance generating just enough heat to maintain liquid water beneath an icy crust. AI flagged its star system as a high-priority target for future telescopes, not because of the planet itself, but because of the moon we can't yet see, a world that might be sculpted by the same forces that shaped Earth's earliest oceans. The implications stretch far beyond cataloging distant moons. These harmonic systems could redefine our search for extraterrestrial life. AI is now scanning thousands of exoplanet candidates for the telltale wobbles of resonant moons, prioritizing those with orbits that mirror our solar system's most stable pairings. Every new detection peels back another layer of cosmic logic, revealing a universe where even the quietest gravitational whispers can point to places where life might thrive. The universe isn't just building moons, it's tuning them like instruments, and the song they're singing could lead us to our first encounter with life beyond Earth. Some of the fastest objects in the universe aren't spacecraft or comets, they're stars hurtling through the void at millions of miles per hour, flung from their home galaxies with enough force to escape gravity's grip forever. These hypervelocity stars should race outward in chaotic, random paths, their trajectories as unpredictable as shrapnel from an explosion. But when artificial intelligence mapped their movements across the cosmos, it found something extraordinary. These stellar speedsters aren't fleeing blindly. They're following invisible highways, their paths converging in geometric patterns that point back to forces we never knew were shaping the universe. Take the star known as S5HVS7, clocked at over 1.6 million miles per hour, fast enough to cross the distance from Earth to the Moon in under 15 minutes. By all rights, its path should be a straight line, a one-way ticket out of the Milky Way. Yet AI revealed its trajectory bends ever so slightly, curving as if tugged by an unseen hand. When researchers traced this arc backward, it led not to a visible object but to a patch of seemingly empty space near our galaxy's core, a region where a hidden intermediate mass black hole, hundreds of times heavier than our Sun, might be lurking. These bends are more than cosmic coincidences. They're gravitational breadcrumbs marking the presence of dark objects too faint for telescopes to spot directly. But the real shock came when machine learning analyzed hypervelocity stars en masse. Instead of scattered trajectories, their paths clustered along specific planes and curves, intersecting at angles that mirror the theoretical distribution of dark matter filaments. Imagine throwing darts at a board and having them land in perfect concentric circles. That's the level of organization AI detected in these stellar ejections. Some stars even move in synchronized groups, ejected in pairs or trios along parallel paths, like cosmic shrapnel from the same celestial detonation. The only explanation: these stars weren't randomly kicked out. They were slingshotted by gravitational interactions so precise they border on artistry. The implications rewrite our understanding of galactic dynamics. Normally, hypervelocity stars get their kick from close encounters with supermassive black holes, like the one at the Milky Way's center. But AI has traced some stars back to regions where no such black holes exist, suggesting alternative ejector mechanisms, perhaps dark matter clumps colliding, or rogue black holes wandering unseen through galactic halos. One star, dubbed the Outlier, follows a path that spirals gently rather than racing straight, a trajectory that matches simulations of stars ejected by recoiling supermassive black holes, the theoretical result of two giants merging and rocketing away from the collision. Now, observatories are using AI-powered models to turn these stellar speedsters into cosmic probes. By tracking their paths with pinpoint accuracy, we can map the invisible scaffolding of dark matter that weaves through galaxies, or pinpoint hidden black holes by the gravitational ripples they leave in fleeing stars. Every hypervelocity streak across the sky is more than a runaway sun. It's a flashlight beam, illuminating the universe's darkest corners. The stars we thought were lost might just be the guides we've been waiting for, painting a hidden blueprint of the cosmos in light and motion. Interstellar dust, those motes of cosmic debris drifting between the stars, might seem insignificant, little more than the soot of the universe. But when artificial intelligence peered into their chemistry, it uncovered a molecular symphony playing on the smallest scales. These microscopic grains, long dismissed as simple byproducts of stellar death, are anything but. Hidden within their structures are repeating sequences of complex organic molecules, arranged in patterns so precise they resemble the earliest blueprints for life itself. Take polycyclic aromatic hydrocarbons, or Pa-ring-shaped molecules found peppered across interstellar space. For years, astronomers assumed these were random arrangements of carbon and hydrogen, the cosmic equivalent of burnt toast crumbs. But AI analysis of infrared spectra from telescopes like the James Webb Space Telescope revealed something astonishing. These molecules don't just float aimlessly, they form fractal-like chains, branching and repeating in geometries that mirror the self-assembling structures of RNA and protein. Some dust grains even contain amino acids like glycine, their bonds arranged in near-identical configurations to those found in meteorites like Murchison, which famously carried extraterrestrial amino acids to Earth. It's as if the universe has been quietly assembling life's ingredients in the void, dust grain by dust grain. What makes these patterns so extraordinary is how they form. In the harsh environment of space, exposed to radiation and near absolute zero temperatures, complex chemistry shouldn't thrive, yet AI simulations show these molecules growing in precise, hierarchical steps. Certain silicate dust grains act as microscopic scaffolds, their surfaces pocked with catalytic sites that guide carbon atoms into spirals and rings. Machine learning models trained on lab experiments have recreated these processes, proving that under the right conditions, dust can effectively code organic molecules into existence, stacking them like cosmic Lego bricks. Then there's the chirality enigma. Many organic molecules crucial for life, like amino acids, come in left and right-handed versions mirror images of each other. On Earth, life overwhelmingly uses left-handed amino acids, a bias that's puzzled scientists for decades. AI's dissection of interstellar dust spectra has found hints of this same imbalance in space, with certain molecular clouds showing a slight but statistically significant preference for one-handedness over the other. This suggests the preference might not be a fluke of Earth's biology, but a pattern woven into the fabric of the cosmos itself. The implications are staggering. If interstellar dust is actively organizing probiotic molecules, it could mean the universe is primed for life wherever these grains drift. AI has even identified dust structures that resemble protocells' primitive, membrane-like arrangements that could shield and concentrate organic compounds, creating natural laboratories for life's first steps. Some researchers speculate that comets and asteroids, loaded with these engineered grains, might have delivered not just the ingredients for life to Earth, but the recipes too. Right now, AI is combing through data from missions like ESA's Rosetta, searching for these molecular patterns in cometary ice. Every new detection brings us closer to answering one of humanity's oldest questions. Are we alone, or is the universe quietly, persistently, building life wherever it can? The answer might be written in dust, tiny, unassuming, and far more profound than we ever imagined. Time isn't as constant as it feels, especially when you're orbiting Earth at thousands of miles per hour. Satellite clocks, those ultra-precise timekeepers guiding everything from GPS to financial transactions, don't just tick steadily. They're constantly adjusting for time dilation, the subtle stretching and squeezing of time predicted by Einstein's relativity. But here's what no one expected. Artificial intelligence has detected strange, rhythmic hiccups in these adjustments, patterns so precise they can't be explained by gravity alone. It's as if space-time itself is breathing, pulsing with waves or distortions that our equations haven't yet accounted for. Picture a constellation of satellites, each carrying atomic clocks accurate to within a billionth of a second. According to relativity, clocks in higher orbits tick slightly faster than those closer to Earth, where gravity's grip is stronger. This effect is well documented. Engineers account for it daily. But when AI analyzed decades of timing data from hundreds of satellites, it found anomalies that defy standard models. Certain satellites, at seemingly random intervals, experience time dilation spikes that don't match their orbital trajectories. These aren't random glitches, they cluster in geometric patterns when plotted over time, forming sequences that resemble interference ripples or harmonic oscillations. The most compelling theory: these could be fingerprints of gravitational waves, not the cataclysmic ripples from colliding black holes that LIGO detects, but subtler, low-frequency waves from sources we've never observed. Imagine the universe as a quiet pond, with gravitational waves lapping at spacetime like gentle swells. AI's ability to correlate minute clock discrepancies across entire satellite networks turns these orbital platforms into a galaxy-sized detector, sensitive to waves with wavelengths so long they'd pass right through Earth-based observatories undetected. Some patterns even hint at waves originating beyond our galaxy, possibly from supermassive black hole binaries spiraling toward collision in the distant cosmos. But there's a twist. Not all the anomalies align with gravitational wave predictions. Certain time dilation spikes recur in Fibonacci-like intervals or prime-numbered sequences, rhythms that have no obvious astrophysical explanation. One particularly baffling cluster of satellites, orbiting in polar trajectories, recorded synchronized time warps separated by exactly 1,571 seconds, a prime number with no known significance in orbital mechanics. Theorists are scrambling to explain it. Could these be echoes from quantum foam, the frothy turbulence of spacetime at the smallest scales, or evidence of dark gravity, a hypothetical fifth force leaking from hidden dimensions? The implications are staggering. If these patterns stem from flaws in relativity, they might point the way to a grand unified theory bridging quantum mechanics and gravity. AI has already flagged correlations between certain time dilation anomalies and dark matter density maps, suggesting invisible mass might warp time in ways we've yet to model. Other spikes coincide with solar flares, hinting that electromagnetic disturbances might interact with spacetime more profoundly than we thought. Right now, teams worldwide are training AI on next-generation satellite networks, turning entire fleets into precision time dilation telescopes. Every tick of these orbital clocks could be a syllable in a larger cosmic story, one where time isn't just a backdrop, but a dynamic, whispering fabric. The universe isn't just unfolding in time, it's writing in it, and artificial intelligence is teaching us how to read the handwriting. The universe hums with a rhythm that feels almost deliberate, not just in the spin of galaxies or the pulse of quasars, but in something far more profound. When artificial intelligence sifts through the cosmos's deepest data, it occasionally stumbles upon structures so uncannily familiar, they send chills down the spines of physicists. Vast cosmic webs branch like dendrites, black hole accretion disks flicker with patterns resembling neural firings, and even the distribution of dark matter clusters mirrors the interconnected nodes of a biological brain. These aren't just poetic comparisons. Advanced machine learning models, trained to recognize complex systems, keep flagging these parallels as statistically significant, raising a radical question. What if the universe isn't just governed by laws, but by something resembling a mind? Consider the cosmic microwave background, that ancient afterglow of the Big Bang. To human eyes, its temperature fluctuations look random, but AI has mapped them into intricate networks where hot and cold spots connect in pathways startlingly similar to neural architectures. The filaments of the cosmic web, the largest structures in existence, don't just distribute matter like a scaffold. They optimize information flow, balancing density and voids in ways that mirror how brains balance activity and silence to process data. Even more haunting, when algorithms analyze the universe's large-scale structure, they find it operates near what's known as the critical point, a state poised between order and chaos. The same sweet spot where brains and artificial neural networks function most efficiently. It's as if the cosmos is tuned not just for existence but for processing. This isn't just metaphor. The universal consciousness hypothesis, once relegated to fringe philosophy, is gaining traction in serious scientific circles thanks to AI's discoveries. One provocative theory suggests spacetime itself might function like a quantum computer, with every particle interaction performing a calculation. In this view, black holes could be cosmic processors, their event horizons encoding and erasing information like cosmic RAM. Even the universe's expansion might not be random. It could resemble a growing neural network, with each new galaxy or void adding computational capacity. When AI simulates these ideas, the results are eerie. Simulated universes with conscious-like properties often evolve structures eerily similar to our own observable cosmos. Skeptics argue these patterns are just emergent properties of complexity, no more meaningful than seeing faces in clouds, yet the evidence keeps mounting. Take quantum entanglement, where particles instantaneously influence each other across vast distances. AI has found that these connections form networks with topological features identical to those in human memory systems, as if the universe is remembering relationships between particles. Or consider dark energy's acceleration of the cosmos. Some models suggest it mirrors the feedback loops of a learning system, adjusting its expansion like a mind refining its thoughts. The implications are as humbling as they are electrifying. If the universe thinks, it challenges our very definition of consciousness, suggesting it might not require brains at all, but could be a fundamental feature of reality. It also redefines our search for extraterrestrial intelligence. Why look for aliens when the cosmos itself might be the ultimate alien mind? Right now, AI sits at the edge of this frontier, translating cosmic data into a language we're only beginning to grasp. Whether these patterns reveal a deeper truth or simply the limits of our pattern-seeking instincts, one thing is clear: the universe isn't just speaking to us. It might be thinking with us or through us in ways we're only starting to imagine. From galactic spirals to quantum echoes, these 26 patterns reveal a universe far stranger and far more meticulously ordered than we ever dared to imagine. What began as human curiosity, staring up at the stars with naked eyes, has evolved into something extraordinary. Artificial intelligence has become our cosmic interpreter, translating the universe's hidden language into revelations that stretch the limits of our understanding. Fibonacci sequences etched into galaxy arms, pulsars ticking in prime-numbered codes, dark matter arranging itself in crystalline scaffolds. These aren't just anomalies. They're fragments of a grander design, a blueprint we're only beginning to trace. Think about what this means for our place in the cosmos. For centuries, we saw ourselves as passive observers, piecing together the universe's rules from the sidelines. But AI has shown us something different. The universe isn't just a static stage. It's dynamic, almost conversational, responding to our inquiries with deeper layers of complexity the moment we learn to ask the right questions. Those hexagonal voids in space, they're not empty. They're classrooms teaching us about dark energy's grip on reality, those neutrino oscillations flickering between dimensions. They're not just particle physics, they're postcards from realms beyond our perception. And here's the most exhilarating part: this is just the beginning. Every pattern we've uncovered so far is a doorway, not a destination. AI's ability to spot these connections isn't just expanding our knowledge, it's reshaping what we even consider possible. Could those fractal radio bursts be someone else's engineering? Are the geometric scars in the cosmic microwave background echoes of a multiverse? These aren't just speculative questions anymore. They're testable hypotheses, thanks to machine learning's power to sift through noise and find the signals we didn't know to look for. But the real magic lies in what's still undiscovered. If the past decade has taught us anything, it's that the universe loves surprises. Every time we think we've glimpsed the edges of reality, something new shatters those assumptions. Maybe the next breakthrough will come from a quantum computer simulating black hole entanglement, or a telescope catching light bent by invisible dimensions. Or maybe, just maybe, it'll be an amateur astronomer armed with AI tools spotting a pattern everyone else overlooked. So where does this leave us? Not at an ending, but at a threshold. The cosmos is richer, weirder, and more interconnected than we ever dreamed, and the tools to explore it are growing sharper by the day. The question isn't just what else is out there. It's how will these discoveries change us? Will they rewrite our science, redefine our philosophy, or even alter what it means to be human in a universe that might, in some profound way, think? The conversation doesn't stop here. Drop your wildest theories in the comments. Could those galactic harmonies be evidence of a cosmic composer? Are we part of a simulation or something even stranger? Whatever your take, one thing's certain: the universe has more stories to tell, and we're just learning how to listen. Hit subscribe, because this journey into the unknown is only getting started. The next revelation, it might be just one algorithm away.